Next
All right.
Jim.
All right, I'm John Heinz, and I'll be doing the lead for the Rankine cycle experiment. First, quick overview of what we'll be going over. We'll be going over the goals and objectives of the experiment, an introduction to the background and theory of the Rankine cycle, the experiment apparatus and procedure, then the necessary measurements that we'll have to take during the experiment, and then just a quick projected results of the experiment. So first, going on to the goals, is to understand how the Rankine cycle works, and then go also into seeing how different things are affected, different parameters such as temperature and pressure will affect the mass flow rate, the turbine, and pump work and efficiency for this cycle. An introduction to this is that the Rankine cycle is an ideal thermodynamic cycle of a heat engine or a steam engine, and what it is used to do is project an ideal or theoretical efficiency for steam power plants and other things like that. Today it's actually represents 90% of the electrical energy produced that we use. It was made by, or established by William Rankine, and that's what it's named after. So going into the background, it's comprised of four main parts: the boiler, the pump, the turbine, and the condenser. At the boiler, heat is pumped into the system, which converts the water into steam. The steam is then pushed, that's raising the temperature and the pressure of this water. Then it goes down to the turbine where it spins a wheel or a generator, and then that will produce work out. After it leaves there, the steam doesn't have enough energy to produce more power. So what happens, it goes into a condenser where it will lower the temperature and the pressure of the steam until it converts back into liquid water. And so to get that liquid water that has very low energy back into the system, it gets put through a pump and sent back to a boiler. This is a closed loop cycle. And this is all the theoretical version, so the Rankine cycle of it. The ideal version, you are going to expect losses in the condenser, the turbine, and the boiler, and the piping because of friction. And through also through the boiler, you're going to have heat losses, which are going to have different effects, like through the pressure losses from friction, you're going to have more power pumped in to make up for that. And for all the heat losses, you're going to have more heat added in the boiling process. So going into the theory, going into further detail of what we just went over, is for the pump from H2 to 1, or H2 minus 1, is how you're going to be able to calculate the work work put in for the pump. And then next you're going to go to the boiler and then comparing the entropy for that from entropy 3 minus 2, you'll get the heat that had to be inputted there. All this, and then the turbine, same as the pump, but on a different location on the graph, and then the condenser, same as the boiler. All this is going to be used, well, to go into your ideal balance of energy, and so that'll allow you to see that all the energy should be conserved in this theoretical situation. But realistically, the efficiency, you're going to have losses. So you're not going to get the work that you put in all the time because of these losses. And so we're able to plug in all the information from the previous slide to find the efficiency of the actual systems. So this will help people that are producing power plants figure out, all right, we're putting this much work in, we should expect this much. And if they're not, they can refine things to find out how they can make it better. Here, we're just comparing an actual cycle to the theoretical Rankine cycle. And as you can see, there are different losses throughout here and here because of either the turbine being irreversible or the pump being irreversible, and also the losses that are taking place. So going through the apparatus for this experiment, it breaks down. There was a lot for this experiment, but we can go over the main parts. We have the data acquisition system. We have the condensing tower that is going to allow the or steam to cool down, turn back into vapor. We have a generator, and that's going to produce the electrical power. We also have the turbine, a fuel source, a boiler, and then a pump to make sure everything's running. All right, so going through the procedure for this, it was a long one. Basically, you want to make sure that everything is drained in the condenser and the boiler. Then you're going to connect in and make sure that the data acquisition system is set up. You're going to perform a fuel check to make sure that there aren't any leaks for safety issues. And then you are going to purge the fuel line of all gas. Next, you're going to power up all the components and then basically preheat it to get ready to run the actual experiment. Then going into the measurements and data acquisition, you're going to record different information such as the water levels that were consumed and condensation that was put out. Also, you're going to have all your information from your DAQ system or DAQ system. And this will all be used in your data reduction to break down. You're going to first plot all of them versus time, and then you're going to choose a specific time so that you can have your data analyzed for that time period. And then we're going to compare all that information so that we can find the efficiency for different parts of the components. Each component is going to have a certain efficiency, and then the max flow rate, and then the overall efficiency for the whole system. So breaking down some quick sample calculations that I went through, making these assumptions, I was able to find a turbine efficiency of 25, which is about what we would think, but then the cycle efficiency was a little bit lower than what was expected. From a conclusion of this, we can see that we'll be able to tell the difference of an actual and theoretical cycle, and then learn how to predict different ways and affect the efficiency of steam engines or different things like that. Any questions?
Let's take our speed break.